So I want to know how your chapter 1 went, because the chapter 1 results will tell me if we need to adjust how we instruct, okay? So quick review for all of you. Chapter 1 tests, please send score. So ask your parents, if they've graded it for you, how did I do? Can you please send it to Mr. Tarfa? If I'm seeing that the average is 75%, then that tells me we need to reevaluate what we're doing, right? So let's see what the average is. Let's see how people are doing on chapter 1. At home, experiment 1.2. You just need some yeast and hydrogen peroxide. You put them together, see the bubbles form. Let's keep that image in your mind. We'll discuss it further. Yes?
Some of us have our tests with us.
Perfect. I'll collect those tests then. That would be great. We'll grade those. I told your parents, we can grade it. Your parents can grade it. It just has to be graded. And I know I got some, I got your emails, but I'm grading yours, right? Liam? Okay, I got it. You say? Oh, I can grade it now? Okay. Okay, that sounds good. Okay, so chapter 1, are there any questions about the flow? Thank you. I'll borrow that. Whenever you do a test, you look at how you did, you look at what you did wrong, and you always do corrections. Even if you get 99%, why did you miss the 1%? Here's why that's important. Because someday that 1% can hurt you big time and lower your next test. Right? So if you have a piece that is missing, so all a correction is looking at, oh, I said the answer was anabolism. Oh, but that's catabolism because it was breaking down sugars rather than building up. Does that make sense? So make sure you always do corrections for every subject. That's very important. Every subject that has clear-cut answers, right? Okay, so chapter 1, I just want to discuss the flow again. You have the comprehensive checks, which you should be doing, even if you copy. Like you don't understand the question, you look at the answer and you're like, oh, I get it. Well, then you have to still write those in your own words. So the chapter review and the comprehensive checks will typically be due when the test is done. Does that make sense? You finish the test and now I can look at our review. Does that make sense? That will also tell me if you studied well. Because if you don't have the answers, like what are you expecting? You're going to get 100 without writing any notes? I mean, are you Isaac Newton, right? Even if you're Isaac Newton, you would have notes, right? And Newton is not my favorite, you guys know, but I use him as an example, right? Because he is undisputedly the smartest man who's lived in the last 2,000 years. So that's why I use him as an example. But even the smartest man needs notes. Okay, we're going to talk a little bit about chapter 2, which is actually very heavy with chemistry. So we need to make sure that our chemistry is solid. You guys will be seeing more videos now because the other biology instructor is actually going to record a lot of the lectures using the same textbook. He's following along with what we're doing, and you are welcome to email him directly as well. His name is Dr. Stephen Hill. I actually recorded a biographical sketch with him, and I'll share that with the class as well. If you have a passion for psychology or neuroscience, he also has specialties in those, or has some training in that, and he can share with you from an introductory level. I am fascinated by neuroscience. Okay, chapter 2 is the next thing we're going to look at briefly here, and then I will have you have some group time. So we're going to talk about chapter 2. That's the plan. So chapter 1 test, send your score. If you don't have your score, if you have the test, I'll grade it. Experiment 1.2 at home, and then I'm going to discuss chapter 2. Are there any questions as far as structure before we talk about content?
What about experiment 1.1?
So that's what I said, that we are missing a strainer, and I want to hold off. And I didn't realize your TA is gone today, and she would have that strainer. So I apologize. We're going to hold off on that for now. Okay? So I owe you that. We're going to do it when she comes back. Yes?
If we do corrections on our test, do we get like extra points, or do you just want us to know what we get wrong?
That's a very good question. That is actually teacher dependent, and you'll see that in college. Some teachers give you the credit, some teachers don't, but it needs to be a lifestyle, period, whether there's a reward. But to answer that question, in maths, I will give back quiz points at any time, all day. Chapter 1 test, whatever your score, you redo the test, you do fine, or you do your corrections, you get the points back. However, I don't support the finals exams having a reimbursement of points. You should still do the correction, but not for the final. Does that make sense? But you could get 100% of every quiz if you do your corrections. For biology, I I have hardly seen anyone do a reimbursement of credit for biology, like giving you back the points. What I will say is there will be extra credit opportunities that you can take advantage of that would boost your score up. So an extra credit opportunity could be like lead a lab or write a lab report on something or write a research paper for fun. Those are other ways that professors, so I'm trying to train you. That's a lot of what college professors will do. Another way that college professors give, so here's the good news. Because of a new faculty member, a biology class can literally be like seriously a college course because he's a college professor. Does that make sense? So we are actually applying for accreditation to grant credit without CLEPing. So you get the credit for just passing the class because he has the credentials. I have the credentials for physics. If you want to take physics, once for credential, I could give you a physics credit. Does that make sense? So that's what we're doing with the school is eventually phasing out CLEPing and giving you the credit when you finish the course, which we have full control over. And then the University of North Dakota or NDSU will take the credit because we're Higher Learning Commission accredited. So that's another piece of the good news. I'll let you know once that stamp comes. If the stamp doesn't come, you just have to take the CLEP test. That's the worst case scenario. But please keep in mind, study hard, take good notes, talk to your group members, do your chapter reviews and comprehensive checks, and everything should go pretty good. Yes?
If you didn't get as good as the grade that you wanted to, what if you retook the test, with your corrections and you knew what you got wrong and decided to retake the test?
That's a good idea. Let me ponder that. Let me ponder what that could mean. I would just say stay tuned for extra credit. So here's one more thing college professors do for extra credit. If there's a guest speaker in town teaching in biology, research, whatever, college professors will tell you if you go to that presentation and watch the presentation, and I could tell you when NDSU or UND or MSUM has a presentation, then you get credit. That shows that you care. Does that make sense? Like you're going to go listen to a professor talk about whatever. Okay. So give me a second to get the extra credit going. Don't be discouraged by chapter 1. Chapter 2, the chemistry of life. Okay, so I want to highlight some key things as you study for chapter 2. When is the chapter 2 test? Well, today we're just introducing chapter 2. Next week is, as I said, we're using appendix 2B, week 3. So let's go down to, next week is the 11th, you guys, 11th to the 15th, and then 18th. Thank you very much to do 22nd. I would say on 9/22, you should please plan to take your test for chapter 2. Everybody see that? That's the date, 9/22/23. Let's plan to take the chapter 2 test. Okay, the chemistry of life. Okay, one of the most important things to understand is that substances are made up of atoms. Atoms, very important. Substances are made up of atoms. An atom comprises of several smaller things. So an atom is the smallest stable unit of all matter, and it is comprised of 3 things. Those things are protons, neutrons, well actually let's go protons, electrons, and neutrons. You could write it in any order, but let's just write them down. Protons, electrons, and neutrons. Okay? Protons are positively charged. Electrons are negatively charged. Neutrons are neutral. Okay? So that's the beginning of chapter 2. We're talking about chemistry, and in order to talk about chemistry, we need to talk about atoms. Atoms are very basic, fundamental pieces comprised of protons, neutrons, and electrons. A level up from atoms, however, is something called a molecule that we have to understand as well. Molecule. So we have atoms and we have molecules. What are molecules? Molecules are a group of atoms that form a unit with specific chemical properties. So molecules are a group of atoms. Okay. So group of atoms with specific chemical properties. With specific chemical properties. Okay. I'm sorry, my chalk is running out. And if you can't see my handwriting well, I will get better chalk next time. Okay. So the chemistry of life, we need to understand atoms, we need to understand molecules. The atomic structure is a big topic of discussion in the history of science. Like, people knew that atoms were there, but how can we best describe them? So there was different scientists in different eras that had different debates about the nature of the atom. One person had a theory, that theory was taken down. Somebody else came with a theory, that theory was taken down. For example, you guys have heard me talk about John Dalton. Dalton had a theory of atoms, right? The British chemist who was a teacher at the age of 12, principal at the age of 18. That was John Dalton, right? Hardworking and diligent young man. That's why I expect a lot more from you guys, right? Because I look at Dalton's story, I'm like, they can do it. He didn't even have Google, and he did it. So Dalton was good, but his theory didn't always hold sufficient explanation. In science, you will notice that pattern. Somebody has a theory, somebody else comes and says, oh, actually, your theory doesn't explain that. So then, as time went on, some of the work on atoms, protons, neutrons, and so on, some of this was going on, think of 1896. That's the time frame when we were able to better understand electrons, for example. Now, Dalton's work was earlier in the 1800s. The beginning of chemistry, in terms of chemistry as a specific science, a lot of that work is actually attributed to a man by the name of Lavoisier. Does anybody know Lavoisier, Antoine Lavoisier? Okay, French chemist. Unfortunately, he was beheaded during the French Revolution, and that delayed chemistry's progress. But Antoine Lavoisier is the one who has given us a lot of basic understanding of chemistry. He wrote a book that helped us understand how to name compounds, which we're going to talk about next. Antoine Lavoisier, I wrote a paper about him if you want to read it. I have his book and his biography. He was a lawyer, he was well established, and now you notice where science and history meet. So then what's going on in France in the late 1700s? Well, some things are happening, there's some trouble, and some people get accused of this and that, and unfortunately some people lost their lives. So when he died in the late 1700s, some people argue, and I would argue, that it delayed a little bit of the progress of chemistry. Prior to this, physics was there, doing its thing. Why? Because Newton was there in 1661 to 1665. So Newton does his stuff, chemistry starts bubbling in the 1800s, Lavoisier dies. In the 1800s, a lot of work happens in physics and electricity and magnetism. But then you fast forward to the end of the 1800s, and now we have a new dawn. Chemistry and physics actually become like best friends. So what I'm teaching you right now, physicists need to know it as well. Isn't that interesting? Because it's kind of like chemistry and physics. Everybody see that? Physicists need to know this. As a matter of fact, how many of you have ever had an X-ray taken before? Okay, did you know that X-rays require electrons to get the X-rays? Because you have to charge up the electrons, kind of like boil them, then you have to shoot them at a very high speed, then they hit a tungsten target, and when they hit a tungsten target, chemical reactions happen and it releases X-rays. That's what X-rays are, but it starts with electrons. It comes from electrons. So electrons are important. Did you know that if you have skin cancer, they use electrons to treat that as well, because it's very good at dealing with surface level cancer. So protons, neutrons, and electrons are used by biologists, chemists, and physicists as well. So that leads us to the atomic model that we use today. In your book on page 30, they give you hydrogen as an example. Hydrogen is the first element in the periodic table. It has one electron, one proton. That's the way hydrogen is. The number of protons you have is equal to your atomic number, right? So this is the atomic number of hydrogen. So everybody needs to have a periodic table for chapter 2 to better understand the place of elements on the periodic table, right? So hydrogen is the first element. It has one electron and it has one proton. So if you were to draw a model of hydrogen, you would put the nucleus in the middle and you will put one electron on the outside, and that's the model of hydrogen. If you were to draw the one of helium, you put two electrons on the outside. If you do the one for lithium, you actually draw a second shell. And that's another day's story. This field of study that we're in right now on page 30, that we're dabbling into for a second, is actually a little bit of physical chemistry. What is physical chemistry? Okay. Physical chemistry tries to explain the phenomena of atoms and so on and so forth using principles that are connected to physics. So it's like it takes physics, it takes chemistry, it takes math, and it's one field. So I like, my first degree was in chemistry, and then I've always done math, written math, tutored math. So I've done that for, I don't know, years. And then physics is my master's degree. So one day I was wondering, medical physics. So one day I was wondering, how could you do chemistry and physics and math? So when I went for my PhD in chemistry, for my 1 year of PhD in chemistry, the 1 year I did, while I was in the program, I was reintroduced to physical chemistry, which I knew. We had learned about atoms and all of that, but I'd never seen some of the, how you could write computer code to explain that. And we did that in this class. What was amazing, though, is when I realized that physical chemistry is basically physics, chemistry, and math. And I was the happiest man they could be because it brings them all together. What else is physical chemistry? Let me give you one more example. Thermodynamics. Heating up this room, boiling your water. That's physical chemistry. Physical chemistry is beautiful, but it is not for children because I still cry from some of those assignments. It is intense, but it's worth it. So 1896 comes along, we get the electron, we have to make sense of all of this stuff. We get into the 1900s, and what is one influential person in the early 1900s that comes around? A German physicist who ended up becoming countryless for a year, but who am I talking about? Albert Einstein. So Albert Einstein gave us an explanation that helps us better understand some of these pieces of electrons in the shell. So let's look at the shell of lithium. So for lithium, you have 3 electrons. Everybody see that? So there's 3. The number of electrons you have in your outer shell, there's a connection between the number of electrons, the number of protons, and your atomic number. The number of protons equals the number of electrons in a neutral atom. In a neutral atom, that is the case. Number of protons equals number of electrons. Everybody see that? But if I steal an electron from you, if you don't have that electron, you have one less than you had, you're now positively charged. Why? Because you've lost the thing making you negative, so you're going to be more positively charged because you have more protons than electrons. If you gain an electron, you will have more electrons than protons, and you will become what? Negatively charged, right? So your charge depends on the amount of protons or electrons you have. Notice none of this has to do with the neutrons you have. Okay, so that's what happened with some of the work that Einstein did. Now, some of you know that Einstein won the Nobel Prize, and I love studying Nobel Prize winners. I'm actually reading a book over the next few weeks about the first Nobel Prize winners, and actually in chemistry. So it's going to tell the story of people who won the Nobel Prize from 1901 to 1910. So I like to know who won the Nobel Prize and why. I love to know why, because it tells me something about what they were trying to go after. So Einstein won the Nobel Prize. He knew he would win the Nobel Prize. You don't know that you'll win the Nobel Prize. If you know that you're going to win the Nobel Prize, you're awed. Because there's so many good scientists around the world, but Einstein knew. Why? Well, several reasons, but one of the main reasons is the work he was doing was very, very important in understanding the atom. And what Einstein discovered is called, there's this idea called the photoelectric effect. We're not going to go into detail. This is one of those extra credit opportunities you can take up and talk about, right? So the photoelectric effect is one of the things he did. So when you go home, feel free to look it up and just get yourself some extra bonus points for the photoelectric effect. So Einstein won the Nobel Prize for the photoelectric effect around 1920 in physics. But here's what's interesting, because some of you are like, well, that's cool, he won the Nobel Prize. He didn't win the Nobel Prize for the thing he's most known for. The thing he's most known for could probably give him another 3 Nobel Prizes, right? That's how influential it was. Now, Einstein only won 1 Nobel Prize. There's only one person to win the Nobel Prize in chemistry and physics, and it was Marie Curie. The only person who has won that, and then her husband also won the Nobel Prize, and then her daughter won the Nobel Prize. They are the most Nobel Prized family, and she also was doing her work around here. We're talking about atoms, and it's going to lead a little bit into radiation. Radiation also began like in 1896. So 1896 is a big year in science. We're talking about the discovery of electrons. We're talking about discovery of radioactivity. Do you see what's happening? 1896 is serious. And Einstein at this time, did you guys know there was a time where Einstein didn't really have a job? He wasn't really a big deal. He was just kind of scrounging. And then he gets a job at a Swiss patent clerk office and he's doing his thing. And then in 1906, 10 years later, the world met Albert Einstein. We're not going to get into detail. He's not my best friend either, but Einstein definitely changed how we think of physics. He showed that Newton was wrong on some things, and that's painful to watch. Okay, so we've talked about atom, we've talked about molecule. Now we're going to talk a little bit about some key terms that you need to know. Compound is another one, and element is another one. If you haven't already answered these from your questions at the back of the book, you will be answering those as well. I'm just going to open to the back. Yep, so when you do your define your terms, you guys will define those. I'm not going to go into detail on that. Okay, so page 30 talks about the atomic model, and it talks about the electron cloud. Some of it does get into quantum physics, but you are spared of all the details. Quantum physics is not funny. Okay, number 31, page 31. Let's go to page 31 now. We take a lot of these things for granted, but there's so much that happens on the microscopic level of atoms and behavior of atoms and electrons. And that's where quantum physics explains this. On page 30 of your book, they mentioned the word electron cloud. They said that electrons move around the nucleus. Electrons move around the nucleus, right? So electrons move around the nucleus in a pattern that is often described as an electron cloud. That's very important. If you don't want to be, if you want to be a physicist, pay attention to that. You're going to need that. Okay, let's move on to the next page. So I've basically summarized page 30 and now on page 31. One of the most important things discussed on page 31 is ionic and covalent bonds. Ionic and covalent bonds. If you were with us last year, you remember we talked about ionic and covalent bonds. An ion is formed when electrons are either gained on something gains an electron or something loses an electron. You either become positively charged or negatively charged. So what is a classic example of this? Table salt. Sodium on the periodic table has 11 electrons, 11 protons. It's not as happy as it could be because it wants to gain a solid full shell on the outside. So let me clean the board here, this part here. Okay, what element is on the board right now? Go ahead. Nope. Liam, you're going to say it too? Helium, right? Helium, okay. So this is helium. We should all know how to write the symbols of the first 20 elements. That would be good. That's helium. Is helium happy? Yes. Why? Because its shell is full. It just needs 2 electrons in its outermost shell. But the second shell needs 8 electrons. So when you add a second shell, now there's 8 electrons. Electrons are like people in houses at specific locations, and you can find them based on a specific address. That's how electrons work. You're going to 14th Street, then you're going to turn on the avenue, then you're going to go into the building, then you're going to go into room 5, and then you find the electron. That's kind of the general idea. Electrons have addresses. Does that make sense? So one of the ways we deal with this is something called electronic configuration. Do you guys remember that from last year? So for example, sodium's electronic configuration is on the board. That's where you find it. 1s2, 2s2, 2p6, 3s1. What is important here to note, we're not going to go into more chemistry than we need to today, is if I lose the 1, each of these numbers represents electrons. So what's 2 plus 2? 4. 4 plus 6, 10. 10 plus 1 is 11. So sodium has 11 electrons, 11 protons, and if it loses an electron, this 3s here is like, think of it like, okay, it's now down to that. This is a full shell. In order for sodium to have a full shell, it needs to lose an electron. Chlorine, on the other hand, is desperately saying, give me an electron. So an ionic bond is formed when one element gives an electron away and another element collects the electron. Everybody see what's going on? It's an exchange that is happening that makes everybody happy. You go to the store, for example, looking for a good math history book, which is a good thing to be looking for. You go to the store and you say, here's my Leonard Euler book is coming today. Anyways, but you basically say, here's $20. They give me my math history book. I'm happy. They're happy. That's what sodium chloride does. They're both happy. And their bond is strong. Everybody get that with ionic bonds? Ionic bonds are stronger than covalent bonds. What is a covalent bond? A covalent bond is formed when the two elements that come together, they don't give, it's not like one gives the other one an electron, it's that they share the electrons. So think of ammonia. They're sharing electrons. They're not giving it away like sodium chloride. So that's an ionic bond. We could look at covalent bonds. Things like water would be a covalent bond as well. Okay? So in your book, they give you examples of sodium chloride, and then they give you an example of covalent bonds like H2O on page 31. Okay, they also define a strong force, which is defined here. One would expect that you would not be, actually they go back to the beginning, but they explain what a strong force is. There's something called a strong force and a weak force. We're not getting into the quantum physics of that. And honestly, part of what helps me as I'm teaching you today is I'm focusing on the pieces that I know you need more of. So we're not actually going to talk about strong forces in more detail because that's not on your test. That's more for fun. Okay? Moving on. There's there's ionic bonds, and what's the second type? Covalent bonds. There's actually more types of bonds. One of them is called a hydrogen bond. A hydrogen bond is described on page 32. In addition to ionic bonds and covalent bonds, a third type of bond is vital to life. Hydrogen bonds are weak bonds that involve the interaction of a hydrogen atom in one molecule with an oxygen, nitrogen, or fluorine atom in another molecule. I remember, Liam, and your group, you guys remember we came up with the word fun. F-O-N. Hydrogen bonds are formed with fluorine, oxygen, and nitrogen. Okay? So remember that in describing hydrogen bonds. Okay, that's the end of section 2.1 in terms of the big terms that need to be known. Let's see. I'm going to pause. The next set of topics are going to focus more on DNA specifically, talking about water, and then DNA. Let me see. Okay, let me end with one more thing. We're gonna spend more time with DNA later. In your books, I want to introduce you to a gentleman at the last page, and I'll give you back page 57. 57. Open to page 57. Another extra credit opportunity could be go find Dr. James Torr's video on the origin of life, and you can watch that for fun. In the scientific community, a lot of people specialize in very specific areas of study. When you get a PhD, it's not that you're going to study the nature of ionic bonds. It's that you're going to study the nature of ionic bonds in a very specific compound, and you do that for 5 years sometimes. Do you tend to be pretty good at it after 5 years? Like, that's all you do. You do nothing else, just that. So when you get a PhD, especially in the sciences, you're very specific to a thing. In the world today, there are few people who are as specialized as Dr. James Torr in your book there. There are few people in the world in nanotechnology and organic chemistry origin of life discussion like the man in that book. If he wins a Nobel Prize tomorrow, I won't be surprised. I doubt he is going to win one just in terms of some of the drama. But I think that he is a very good candidate for that. James Torr and some of his work is breaking ground in the field of chemistry, organic chemistry, and he's doing amazing work. He works with graphene. They're building things for medicine. They're doing amazing work. But here's what's the coolest thing ever. One of the leading organic chemists in the world today would go to give a lecture, okay? And he would literally kneel before the audience and say, if it's okay, I'm going to pray first and then just share my Jesus with you before I teach. The leading organic chemist, one of the leading organic chemists in the world today, is a devout Christian, unapologetic. He came to Minnesota. They invited him to give a lecture at a school. He's at Rice University in Texas. Like, this guy and John Lennox, right? I watched a discussion between the two of them. My IQ went 10 points up just watching the lecture. Like, my IQ doubled. I'm like, it was like the internet almost broke. You can't put them in the same room, but they did. These people are smart. But James Torr said to them when he was giving this lecture, I love Jesus, and I want to tell you about Jesus. Email me, and I will have a Zoom call with you, one-on-one, if you have questions about Jesus. And now I'll share with you about organic chemistry. Listen to one of his lectures and you'll realize, no, this guy is serious in his chemistry, but he's also serious in his faith. He inspires me. James Torr inspires me and shows that you can be like James Clerk Maxwell today. You can be the best in your field and love Jesus, and that's just fine. And the fact that he will make time to meet people on Zoom calls, I'm like, that could take a lot of time, but he makes that time. And then he teaches Sunday school, which you could actually Zoom into in Texas and watch him chat. He loves science and faith discussions. So be encouraged, everybody, that one of the leading people in the chapter you're leading in the world is actually a follower of Jesus. That's very encouraging to see. In a time where people tell you, you can't be a scientist and a Christian. It's like, look at the guy over there doing science that nobody in the world is doing. He knows the science and he loves Jesus. So the work that James Toy is doing, which is discussed in chapter 2, you get into that more. And next week we'll talk about DNA. We'll talk about carbohydrates and proteins and lipids and so on and so forth. The building blocks of life. Everybody get that? That's what we're talking about next week. The building blocks of life. And those are connected to even the food you eat. You need carbohydrates, you need fats and oils, you need lipids, you need proteins. Everybody see that? That's what you're going to be talking about next week. And then how does all of that happen? And let's now get into DNA. Why do you look the way you look? Why do I look the way I look? Now, there's certain things that are not encoded in DNA necessarily, but some things are. My hair color, right? There's certain pieces of who people are. Okay, practical application, and then you split to your groups. When a crime happens, sometimes years later, forensic scientists come back and they say, we know who did it. Have you guys ever heard those kinds of stories? And what do they say sometimes? DNA. And then it's like, but how did you know that it was that person? Yeah, I don't want to get into drama. I don't watch bad crime movies or anything. I don't watch movies pretty much. But what I wanted to say is there was a bad thing that happened in the West Coast in the US last year. Terrible. And the person who did it actually fled to the East Coast. There's no way they would ever find this person. But they went to the crime scene. They gathered as much as they could. The person did things they shouldn't have done, had gloves, all that. But then all of a sudden, the city is in mourning in the West Coast. All of a sudden, yeah, we got him. Like, we have him. Like, no, we're good. Like, people are like, how can you know for sure? Well, we found some piece of a strand of possible DNA. We linked it to some distant relative. We went to their trash can in their state where they were hiding, and the DNA linked. I didn't know they search people's trash cans randomly until I read that, and I thought, that was fascinating. That was how they found the person, and they transported him all the way back to the West Coast, and now he's facing trial. DNA is so specific that they used it to his distant relative and then traced it back to him. We all have DNA, right? We all have DNA encoding different things about us. And it's the beauty of the creation story that all of us are unique, that unique. Like, you're so unique, there has never been you and there will never be you. You're the only copy of you. Like, live well. Don't compare yourself to somebody else. Yes, we all have quirks, weaknesses, problems, right? But use your strengths to encourage others. And remember, you are the only copy. We don't have any other copy of you. We need you to be you functioning well. Amen? Okay, we're dismissed to our small groups, 15 minutes of answering questions in your books. Whether it's the comprehensive checks or the chapter reviews.